Hi, in this video, we want to take a look at model misspecification. So we're going to consider two types of situations. One where we underfit our model, that is that we've missed variables that we should have included, whether that we chose to do that or we didn't have the data to be able to fit the proper model, or we overfit, that is we have too many variables in there. Now we're not going to consider the situation where we miss some and include ones that we shouldn't. We're just going to keep it relatively simple. All right. To summarize what's going to happen, and if we underfit, we make things biased. If we overfit, we increase the variance. And so that's basically a good way to summarize the penalties that we're going to see. All right, so we're talking about model misspecification. Let's consider the consequences of specifying the wrong type of model. So let's say that y is equal to x times beta plus epsilon. And I'm going to say that x, throughout this video, I've got x1 and x2. So x1 is like what's in there every single time. So x2 will be either what we dropped out that we should have had, or what we included when we should not have. And so it's going to depend on if we're talking about underfitting or overfitting. And then beta is going to be beta 1, beta 2, corresponding to the x's. Okay, so here, this model is y equals x1 beta 1 plus x2 beta 2 plus epsilon. So when I'm underfitting, this is the part I include, this is the part I missed. If I'm overfitting, this is the part that I want to keep, but this is the junk that I put in there that I shouldn't have. So we've got two ways to approach this. All right, and now, whenever I'm doing this, I'm always going to say that the betas are not equal to 0 to fit the logical argument correctly. All right, so first let's look at underfitting. For underfitting, let's say that the true model is going to be y is equal to x1 times beta 1 plus x2 beta 2 plus epsilon. Okay, but we make the mistake that we say that y is equal, that we fit the model y is equal to x1 beta 1 plus epsilon. Or either it's a mistake, I omitted variables I should have kept, or I just didn't have the data. Maybe there are variables I should have had in there that are not available. That happens, right? Okay, so this is what the true model is, but this is what I'm going to ultimately generate. Well, what's going to be the penalty? What's going to be the mistake? We want to know beforehand. Now, if I'm overfitting, what's going on is our true model is y is equal to x1 times beta 1 plus epsilon. And then our model, what happens here, we're overfitting, we're including variables that we shouldn't. So we have all the correct variables are included, but we throw in some crap additionally. All right, so let's look at first theorem. It's going to cover underfitting. Let's say that the true model is involving x1 and x2, but I don't have the x2 variables in my model. Now throughout this, we're going to go ahead and assume that our covariance is the sigma squared times identity matrix, so that's nice and easy. Now, when I do my fit, my beta 1 has, so whenever you see a star in here, there's a mistake. The textbook uses the notation of star is what I have, but it's not what I should have. It's what I'm incorrectly using to to understand what's going on. Okay, so here I'm taking a beta 1 hat star, and I'm just fitting everything as if this was the correct model, and this is the estimate that I would get. All right, in this situation, what's going to happen is that our expected value of beta hat star 1 is going to be beta 1. That's good. All right, we like that. But there's some junk tacked on. It's going to be this bias right here. So this will be the bias term. Well, what is this bias? Well, it's going to be this matrix here, A1 transpose X1 transpose X1 transpose. All right, that should be really familiar at this point, times X2. Then we're going to multiply by the coefficients of the variables that we missed out on. And that's going to give us our bias term. Now, the covariance on the incorrect coefficients estimates that or that we get but we shouldn't have is going to be, it's going to look a lot like the coefficient for regular beta. It's just that you'll notice that I've got the x1 instead of x. All right, so something to notice is that the bias term depends on the x values, and you'll notice it doesn't depend on the y's at all. And it uses both parts of that x matrix, x1 and x2. Okay, well, how do we prove this? Well, for the expected value, I just take the expected value like I would normal. So this is my estimation formula right here. Well, I take the expected value. The x's are treated as constants. So since they're constant, I can pull them out of the expected value. Now I just take the expected value of y. Well, I know what the expected value of y, because that is the x1 beta 1 plus x2 beta 2. That's the true correct model. Okay, so now I just go through and I distribute, boom, boom, and boom. All right, I look through this part right there. I notice, hey, that's going to cancel out because here's an inverse and the the corresponding matrix that cancels out to be beta 1. Now here, this is that A that I referred to earlier, and then beta 2, and then boom, we've got it. Now for the covariance we go through and we grab the formula once again. So what I'm going to do, I'm going to go, the covariance of our coefficient estimate is exactly, the way that the formula for finding the estimate. Well, I've got a formula when I have a matrix times a vector for covariance. So I have a matrix, which is involving all these x's, times y, which is the random term in this part of the formula. Remember, the x's are treated as constants. All right, so this, all I do is I apply the formula. I pull it out front, and then I take the transpose and put that to the rear. Now remember, this will be symmetric, so the transpose disappears. Okay, so when I pull this out front, I get this part. When I take the transpose and put it to the rear, remember, transposing switches the order. And so taking the transpose on that goes there. This is symmetric, so that goes there. So now I have the covariance of y in the middle. Well, what's the covariance of y? By assumption, that's sigma squared times I. So this is sigma squared times I. I went ahead and just factored out the scalar, and then multiplying by I does nothing. Then I notice I have an inverse, and the thing that it's the inverse on, so I know that cancels out, and boom, we've got it. All right, so punchline. When underfitting, the coefficients will be biased. So my slope estimates will always be biased. Now, unfortunately, we won't know which direction because we don't know what the x2 values are. But if I have like x2, if I have variables that, or if I have fields that I'm considering on including, but I go ahead and don't include them, I could actually go ahead and work out the estimated bias off of this, right? Or at least get an idea. All right, so here's what's called the alias matrix. So we can, if I have x1 and x2, so here, if I'm in a real life situation and I'm going, okay, I'm thinking about these two sets of predictor variables. I've got x1. I may or may not use x2, but I'm going to use x1 for sure. I can look at the alias matrix and get an idea of what the bias would be like if using x2 is the correct model. That way I can make a better informed decision. All right, well, a corollary of this, if this is what's really driving that bias in there, if I know that x1 transpose and x2 is equal to the 0 matrix, then the bias is gone. So if I'm in a situation where I have two sets of predictor variables that are orthogonal to each other, then leaving one out is not going to make the coefficients bias on the other ones. This is nice. So if x1 and x2 are orthogonal, then the expected value of the underfit coefficients is going to be what we want it to be. So in this situation, I can trust the slope estimates if all of the missing predictor variables are orthogonal to the included predictor variables. Now, if they're not orthogonal, then I've got a bias issue, and that's just how it is. All right, so now let's take a look at overfitting. So now, overfitting, what we're saying is that I have all of the correct predictor variables included. I went and I included some junk in there that I should not have. Okay, so how the textbook denotes this is that they go ahead and say x sub 0 is a particular observation of your data. Okay, so this is a row on your data matrix. And they go ahead and say that vector x01 corresponds to the x1 matrix, and then vector x02 corresponds to the x2 matrix. So this way they group up the variables that we have, and they group on the observations. They group up the ones that we include in the model and the ones that we shouldn't have included in the model. All right, so if I overfit, so if y hat is equal to 0, 1, and you notice that this is the incorrect coefficient, so this is after I overfit. So let me back up. Is that right? All right, so here y hat 0, 1 is equal to x01 transpose. So here, let me back up. This is what we should be using. If I take this dot product, and where this is how that's calculated, and we're saying the beta sub 2's are not equal to 0, then the expected value of this business is going to be, this is very similar, beta 1 plus a beta 2 from what we had previously times the x01 vector transpose. And then I can rewrite this just using the formulas from previous, and we can see that we get what we want plus some junk over here. So here we can see that this gives me a representation of how my expected value will be off when I overfit. So we can see that there's going to be a problem on our predicted values. Now, if I overfit on my variance, so here's what beta hat is, and you notice that here I have x1 and x2 in here, and then here's beta 1, beta 2, and here's beta 1 star hat, and we fit it this way. Then I see that we have a formula on the difference on the covariances. So here is what I should be getting for the beta 1 values. You notice that the beta 2 is not addressed in this. And here's what I actually observe on the coefficients on the beta 1s. And this gives me a formula for an idea of how what the difference between what the estimated covariance should be and what it will be. A is the alias matrix, and then B is this guy right here. So this formula is coming from the partition matrix formulas, kind of ugly. Well, we'll see that our variance estimates or the actual variance values are going to be off, and we can see that the variance on the dot product will also be large. So how do we prove this? All right, so I worked out a good portion of these details before I conclude that this just isn't worth slugging through in a video. No one would pay attention by the end. I was doing it on scratch paper. I got down to here. I started doing it on scratch paper where I worked through it. And I realized I just put you to sleep if I try it. But I'll show you how to get started if you're really interested. If you really are excited about it, we can sit down and we can go over it. It'll take a little bit of time just because the hardest part really is converting between theorem 2.50's formulas and the presentation of the block matrix that we have. It's basically just a slug it out proof. You just go through, use theorem 2.50 and just keep going through without making a mistake. You'll get it. I don't feel it's very informative, but how you would proceed to get this knocked out is you say that X is the block matrix. So then you know what X transpose X is, and you know what the covariance of this is going to be. And so then you apply the inverse to that. So now the inverse, you know, it has a formula for block matrices. You apply that and you just start working through. Something to be aware of is that the B in this formula, in this theorem is different than the B in the formula in theorem 2.50. So you have to be real careful in stepping through. But this B is different than the B in theorem 2.50. So just be careful, work through it if you want. I think it's okay to skip this one. All right, so to prove this, once again, we use theorem 2.50. It's slightly different, but it's really conceptually the same. You know, we just end up working through this matrix, and then we work through multiplying on each side. It'll work out, but it takes a bit. All right, so now let's take a look at what happens if we underfit and our variance estimate. So let's say that y is equal to x beta plus epsilon, but we use a reduced model. So we're missing something. We're missing the x2s. All right, well, this x of 1 squared, this is going to be my actual estimate on the variance. Okay, so what do? What our expected value is going to be the expected value of, or what we want our expected value to be, plus this bias term over here. Now, if I look at this bias term looks a lot like, you know, something from the hat matrix discussion, but it's on the x1s, and I've got this x2, beta 2 on each side of it. Okay. So, you know, this is a very natural way to proceed. So what we're going to do, we're just going to focus on the numerator, and I'm going to just take the sum of squares error formula, and I'm going to rewrite it using the matrix formula. So now notice that this is a sum of squares error on the model that we've built, not the model that we should have, because I have all x of 1s in here. All right, when I have this presentation, I realize I have like the random part on the left, random part on the right, and I have a constant matrix in the middle. That makes this a quadratic form. Okay, if it's a quadratic form and I'm taking expected value, I have a formula for that. Okay, so remember that if I have a quadratic form, y transpose my, then it's going to be a trace, and then I take the expected value on the left, the matrix expected value on the right, and I get it. All right, so at this point, it's just, we have the formula. It's a just slug it out method. All right, so we have a trace part, and then we have the expected value on the left, expected value on the right, and then we start working through this. Okay, so the trace, so something that's key to this is that I have the identity matrix, so I've got sigma squared. Remember, sigma squared times this stuff is inside a trace. The trace is an addition, so I know that I can factor out that sigma squared. So that's how the sigma squared ends up here. That's how the sigma squared ends up here. Well, trace is an addition operation, and I've got subtraction on the inside, so I can break up the trace like that. All right, so now I have the trace on I, which this is the n by n identity, and then I have the trace on this. All right, remember, the trace is commutative on the inside, so I can change the order of stuff in here. If I can change the order, I can rewrite this so that I have x1 transpose x1 times its inverse. Then boom, I get the identity. Well, what's the size of that? Well, if I think about it for a moment, after I move this over, that's x transpose sub 1. All right, well, that is going to have k plus 1 rows, and I have x sub 1 has k plus 1 columns. So this will be the k plus 1 by k plus 1 identity matrix. And so that's how we get this part right here. Now, this part, the upcoming part on this is a little bit trickier, and it takes a lot more multiplication. It's going to work out that a lot of stuff is going to cancel out. You'll notice that right now, as it stands, everything is involved. I've got x over here, I've got x over here. But as I proceed, if I look up at this, I've got x sub 2, x sub 2. what's going to end up happening is a bunch of stuff is going to cancel out. It's going to be beautiful. It's going to be great. And so really to get it, you just have to slug it out. It's long, it's tedious. It's not that bad, but if you're someone if you're a PhD student, you really should tough it out. You need to be able to work through this type of stuff. I feel like this is the kind of thing that you need to suffer in silence on. I did plenty of suffering in silence during my PhD program. I'm going to put it on your shoulders this time. All right, so if I want to summarize everything from this, if I underfit in linear regression and all the variables I use should be there, then I'm going to have bias coefficient estimation. So I can't actually trust the slope, even though I won't know I can't trust the slope. I'll have bias fitted values, and I'll have bias variance estimate. Now, if I overfit, now when I say overfit, everything that should be there is included. I've got some junk added on. Then I'm going to have increased variance on the coefficients, and I'm going to have increased variance on the fitted values, or the increased variance on the fitted values. That's a problem, because when I if I'm going to use this as a predicted value, or sorry, a predicted estimation of the future, I can lose my freaking job over that. All right. So that's all I've got for you. Take care and goodbye.